So, eigenvalues and eigenvectors of general bigger than 2 by 2 matrices. So, remember that with a 2 by 2 matrix, we just found the expression A minus lambda I, found a determinant, and we got 2 eigenvalues. And then from there, we were able to put it back into this equation to find the eigenvectors. So that's the process we're going to do, except we're going to do it for larger matrices now. And the step-by-step process for finding eigenvalues and eigenvectors would be to first to compute the characteristic polynomial, set it equal to 0, and solve for that. And then once you find the eigenvalues, you will find the eigenvectors associated with them, and then that would define your eigenspace for a particular eigenvalue. All that makes sense? Sounds a little confusing, but when we do an example, we'll see it a little bit clearer. A couple of other definitions here. You know, when we solve for quadratic equations or any polynomial equations, it's possible that we might get a repeated root. So we say that root has multiplicity 2 or 3 or whatever. So whenever we run into something like that with multiplicity, when solving for the characteristic polynomial, we call that the algebraic multiplicity. Now, a lot of times, that algebraic multiplicity, say, has multiplicity 2, means that you're going to come up with 2 linearly independent eigenvectors. And so that's going to be your geometric multiplicities. The number of eigenvectors that you get for an eigenvalue will be your geometric multiplicity. Okay? So again, we'll try to make sense out of these definitions and step-by-step processes when we do an example. So let's do an example. Let's see if we can come up with a 3 by 3 matrix or something. 4 by 4? No. Let's start with a 3 by 3 matrix. Number 5 or 6? Maybe we'll do number 6. So the idea is to find the eigenvalues and eigenvectors and eigenspaces and define multiplicity, geometric multiplicities, and stuff like that. So this is our vector, or our matrix, and we want to find the characteristic polynomial. So we want the determinant of A minus lambda I and set that equal to 0. All right. So I'm going to go ahead and jump to this, finding the determinant A minus lambda I. And I don't know if you remember, but when we were doing this some time ago, I think it's clear that the I is the identity matrix, and so that's just a diagonal. So each one of these diagonals will have a minus lambda times 1, or minus lambda. So it's essentially the same thing as the original matrix, except along the diagonals you'll have a minus lambda associated with it, going along with it. So everything else will remain the same. Except for the diagonals with the minus lambdas all across. So our next step is to find the determinant of this, and then that's gonna give you your characteristic polynomial. So remember how to find the determinant of a 3 by 3 matrix is we want to expand on any row or any column and then find the submatrices associated with it. So I'm got my eye on the second row because it has zeros in it, and the associated signs with that, we've got a minus, a plus, and a minus. So we have our determinant is going to be an expansion along this. So we have a 0 for the first one with a negative sign, plus 2 minus lambda for the second one, and then the submatrix for that is 1 minus lambda, negative 1, negative 1, 1 minus lambda. And then on our last one is 0 again. 0 times anything is 0, so we can just ignore that. So here's our equation coming along here, our polynomial. We're going to get 2 minus lambda times the determinant of this 2 by 2 matrix, which we should know how to take. That's 1 minus lambda times 1 minus lambda minus positive 1. So here is our characteristic polynomial. So we want to expand this, solve for this, and hopefully it'll be something. This is going to be a third-degree polynomial, so we have to be a little bit resourceful in trying to figure out its roots. So we're going to set this equal to 0. We're going to want to multiply things out here. 2 minus lambda. This is 1 minus 2 lambda plus lambda squared minus 1. So it looks like the 1's disappear. And then let's distribute some stuff. Minus 4 lambda. Where am I? Okay, minus 4 lambda plus 2 lambda squared minus 2 lambda squared, and then negative lambda cubed. Hope that's right. Does that look right? I'm going to keep going. If it's wrong, just yell and say something. So I can take a lambda out, I think, and then I can combine these two as well. So if I take a lambda out, I'm gonna take a negative lambda out, just so I'm used to having the first term in my quadratic a positive. So this one is going to be lambda squared, positive after I take lambda out. This is negative 4 lambda squared. I take a negative lambda out, so that's going to be negative 4 lambda. Because I took the lambda as negative, and this one will become positive 4. So I think I have minus lambda, and this is lambda minus 2 quantity squared. Is that right? All right. So I got 2 eigenvalues. One of them is 0. The other one is 2. And because of this multiplicity, we say the eigenvalue 2, e value 2 has, and they call this the algebraic multiplicity, algebraic multiplicity of 2. And 0 is an eigenvalue that has algebraic multiplicity of 1. Okay? Yes?
If there were more than one alpha coefficient, would it have enough force to equal 0?
What do you mean?
Like if 0 made equation 0 in multiple locations.
Yeah, so I would have a lambda squared here, and then that would have multiplicity too. Yeah. All right. Yes?
What is the behavior of 1?
This has multiplicity of 1 because it only appears one time. So you guys know what multiplicity is, right? If you factor something out, if you factor like x to the third, x minus 2 quantity squared, and then x plus 1, something like that. And the whole idea of these, when we're taking a look at multiplicity, we're taking a look at the roots, or when this thing is equal to 0. So if you set it equal to 0, you're going to get values for this. You're going to get x is equal to 0, x is equal to 2, and x is equal to -1. Right? So the powers of these things are the multiplicity. So you got x is equal to 0, multiplicity 3, x is equal to 2, multiplicity 2, and then x is equal to -1. Well, if it has multiplicity 1, we don't bother saying it, but it's understood to have multiplicity 1. So that's how many times it occurs. And if you graph this polynomial, you'll see some interesting factors of this too. Its multiplicity of 2 means it bounces up. It looks like a parabola at that point where it touches the origin or touches the x-axis. This is a cubic function. It looks like a cubic function around 0 if you zoom in, and this is just passing through -1. So those are all polynomials with multiplicity, and you count the multiplicity that way. Okay? All right. So that's the first part of doing these problems. The second part of doing these problems is to find the corresponding eigenvectors. So you have an eigenvalue. Now we need to find corresponding eigenvectors. And so what we need to do is we need to take our eigenvalue that we found and then figure out what happens when we set the system equal to 0. Okay? So if we take a look at this, it says compute the characteristic polynomial, find eigenvalues by solving for the characteristic polynomial equal to 0. For each eigenvalue, find the null space. So it's this equation over here, and then that's going to be your eigenspace, any non-zero vectors that you get, and then however many, if you have one eigenvector with that eigenvalue, then that's a one-dimensional eigenspace. If you have more than that, then you have a multi-dimensional eigenspace. All right, so let's take our eigenvalues and put that back into the equation to find our null space. So let's go to the next page for that. Let's keep this. So we need to do this a couple times. Maybe let's split the screen up in half here. Let's figure out what happens with the null space of this. The null space of the matrix A minus lambda I, where lambda is equal to 0. So lambda is equal to 0, and then your matrix then will change to 1, 1, -1, 0, 2, 0, -1, 1, 1, minus, and I have to multiply this by 0, so it looks like it's just a 0 matrix. And then that gives me this A minus lambda I. That gives me this exact same matrix A, and now I want to find the null space of that. Remember how to find the null space? It's like a system that's set equal to 0. So we'll find our system. And then we'll do the row reducing thing that we need to do to get it equal to 0, and then find the null space. Okay, we should be guaranteed to get at least one vector out of this, maybe more. In this case, one of these two vectors will probably give us more than one. So let's figure this out. I think I need to do an R1 plus R3 and replace R3. So if you add that, I get this. If you add 1 plus 1 is 2, and then 0 again. Well, this one doesn't have any. So if we take this, I want to take R2 and then negative of R2, negative 1 times R2, and add it to R3. 1, 1, negative 1, 0, 2, 1, 0, 0, negative 1. Say it again? Oh, how did that happen? Well, then that would totally eliminate this, which is what I was hoping for. All right, so now that that's gone, we have a free variable in x3 or z or whatever you want to call that. So if we're solving for this x, y, z, let's say z is a free variable. And then that will give us our y, 2y is 2y plus z is equal to 0. So y is equal to, let's bring the z over to the other side and divide by 2. And so we get, and then I change my z into a t. So I think it's negative 1/2 t. Something else, Daniel? Thank you. All right, now that's better. So we were solving for y. We get 2y plus 0 is equal to 0, so that just gives y is equal to 0. And then the last one, our first line over here, x plus y minus z is equal to 0, y is equal to 0, and z is equal to t. So bring the t over to the other side. X is going to be equal to positive t, right? So our eigenvector is going to be, well, let's just finish this as a solution for the null space. So the solution for this, finding the null space, is x, y, z equals t times, and then the x is equal to t, or 1 times t. The y is equal to 0, 0 times t, and then the z is equal to t, 1 times t. Okay, yes? Well, when you say your eigenvector, you don't want any variables hanging around there. So if you kept the t in there, that's fine. But then when I want to find the eigenvalue, then I want to take the t's out. So our eigenvector is going to be 1, 0, 1, for the eigenvalue 0. And then just to rewrite this in a slightly different way, eigenspace E sub 0, 0 is your eigenvalue, is going to be the span of this vector 1, 0, 1. Okay? So this is a one-dimensional vector space, which means our geometric multiplicity is equal to 1. Okay? All right, so that constitutes about a third of this problem. And we got one more eigenspace to find, and we want the eigenspace for 2. Was it 2 or negative 2? 2, positive 2. All right, let's try to do that one now. So lambda is equal to 2 is your other eigenvalue. So let's get our matrix set up, the A minus lambda I matrix, and then we're going to find the null space of that. So we have 1, 1, negative 1, 0, 2, 0, negative 1, 1, 1, and minus, we have 2 times I, so 2, 2, 2, 0, 0, 0, 0, 0, 0 on the non-diagonal parts. You could probably skip this step next time, right? So we have 1 minus 2. What's 1 minus 2? That's negative 1, 1, negative 1, 0, 0. Oh, this whole thing disappears. And then negative 1, 1, and then 1 minus 2 again, negative 1. Uh-oh. The whole thing disappears. Well, not the whole thing, right? So when you row reduce this to find the null space, we see that the whole bottom disappears, right? So we got 2 rows of zeros. So that means we probably have 2, what's it called? Free variables. So we'll start off letting our z equal to t, and then our y equal to s or something. I suppose we can just use z and y too, but we're kind of used to doing that. And then our equation then becomes negative x plus y minus z is equal to 0. So let's see, negative x plus s minus t is equal to 0. Let's bring everything to the other side and change the signs. So this becomes a positive s, and this becomes a negative t. So let's see, our x, y, z is going to become s minus t, s, and t, which means if I break this apart with an s first and a t second, I'm going to have a 1 times s, a 1 times s, and a 0 times s. Negative 1 times t, 0 times t, and positive 1 times t. So these two vectors pretty clear. They're linearly independent. These two vectors are linearly independent. And so you have two eigenvectors associated with the eigenvalue 2. So E vectors -1, 1, 0, and that's +1, 1, 0, and then -1, 0, 1 for the eigenvalue lambda is equal to 2. And so your eigenspace we would call this E sub 2 for the eigenvector, or the eigenvalue 2, is going to be equal to the span of these two vectors, 1, 1, 0, and -1, 0, 1.
You have to do this whenever. You don't have to offend you.
Okay, we have eigenspace figured out. So it all comes back to looking for the null space of that new matrix. And then, one more note here. Lambda is equal to 2 has geometric multiplicity of 2, because it's two-dimensional eigenspace, and so in this case it matched our algebraic multiplicity, but it's not usually the case. Is that? I guess it's more common that they match than not match. So there are going to be some cases where your eigenspace might just be your geometric multiplicity might be 1, and then your algebraic multiplicity is 2.
Maybe like reverse for some
I don't know. I think it's more common that the algebraic multiplicity is greater. Yeah. All right, let's move on. A lot to talk about. We can do number 10. I mean, we got a theorem that talks about a triangular matrix, so it's a diagonal. Let's just start it and well, let's get this theorem set up. So it turns out that eigenvalues of a triangular matrix are simply the entries in the diagonal. And so let's see how that applies. So let's do this as an example, and maybe we won't go through the whole eigenspace business, but let's just take a look at the eigenvalues at least. So the eigenvalues are the determinant. So we need the characteristic polynomial, our poly, and that is going to be the determinant of A minus lambda I. And so this is A, minus lambda I. So you're going to subtract lambda from each of the diagonals. You got 2 minus lambda, 1, 1, 1, 0, 1 minus lambda, 2, 3, 0, 0, 3 minus lambda, and 3, and then 0, 0, 0, 2 minus lambda. Now, when we're finding determinants, remember, if you have the determinant, this is a little bit different from the determinant theorem. The determinant theorem just says the determinant of the matrix of the product of the diagonals. And so what we're going to do is, in order to find the determinant of this, we're going to find the product of the diagonals and not worry about anything else. So the product of the diagonals is equal to 2 minus lambda, 1 minus lambda, 3 minus lambda, and 2 minus lambda. And nothing else aside from that. So that was our determinant theorem about the triangular matrix. And so the solutions for this, if this was set equal to 0, this is already in factored form, right? So because it's already in factored form, we just find out when it's equal to 0. You set each of these factors equal to 0, and you get lambda is equal to 1, and 3, and 2, which is exactly the diagonals, except 2 happens twice, so we say this has algebraic multiplicity of 2. And the others are just regular roots with no multiplicity, so if you want, you can label it as algebraic multiplicity 1, but we don't need to. Okay. So I'm wondering if this is easy enough to find the eigenspaces for. Let's find the eigenspace for 2, just because it has algebraic multiplicity 2. It might be just a good exercise to see. Let's find E2. And so I want to set up a new matrix and then find its null space. So the new matrix would just be each of these diagonals minus 2 when lambda is equal to 2, right? So the diagonal minus 2. So that's 0, 1, 1, 1. And then I have a 1 minus 2. It's a negative 1, isn't it? Negative 1, 2, 3, 0, 0. And now I have a 3 minus 2, which is 1. And then another 2 minus 2, which is 0. All right, well, it doesn't look like I'm going to be able to get rid of too many things. My first variable looks like it's going to be a free variable because there's a 0 there. And I can row reduce the second row and the third row, but I think in terms of what's happening here, I think we have 2 free variables, and the other 2 variables we'll have to be able to get. So should we row reduce? Let's just do 1 or 2 steps of row reducing. So I'm going to combine R1 and R2, replace R2. So 0, 1, 1, 1, 0, 0, add 1, 3, and 4, 0, 0, 1, and 3, 0, 0, 0, 0. And now if I switch rows or multiply or do whatever I need to do, what'll happen. I think I'm going to get 0, 1, 1, 1, 0, 0, 3, and 4, whatever. 0, 0, so 1/3. And this is going to be a number, whatever that is. And so what I'll have is I'll have my x1, x2, x3, and x4. It's going to be my solutions. So I'll have x4 equal to 0, because this is some number times x4 is equal to 0, so x4 is going to equal to 0. I have 3 x3 plus 4 x4 is equal to 0, but since x4 is equal to 0, that whole thing is going to go away, so my x3 is also going to equal to 0. And then here, the other two are my free variables. I have x2 is free, and then x1 is another free variable. Wait, is it? No, yeah, sorry. Looks like x2, I can solve for x2, right? x2 is equal to 0. And then I only have one free variable, x1 is equal to t. So I have one free variable. So here I have t times 1, 0, 0, 0. So that's my only eigenvector. So only one E vector. So the eigenvector is 1, 0, 0, 0. Because I kind of jumped ahead, and I was trying to jump ahead and trying to solve. But if you say x2 plus x3 plus x4 is equal to 0, and x3 and x4 are equal to 0, that whole thing's going to disappear. So our E2 is equal to the span of only one vector. And so the eigenvalue of 2 has geometric multiplicity. Of only one, because it's a one-dimensional eigenspace. We only found one eigenvector. Okay. So here's a good example where you have algebraic multiplicity of 2, but your geometric multiplicity is not the same. It's equal to 1. Okay. All right. So that was a good theorem. And so if we have an upper triangle and matrix, we don't really need to do any work. All we need to do to find the eigenvalues is to look at the diagonals. And then you can see by the diagonals if something has algebraic multiplicity more than 1. If that number occurs in a diagonal more than once, then we have an algebraic multiplicity of more than 1. Okay, let's there's this other one over here that really follows a bigger theorem. So this talks about invertible matrices, a square matrix that's invertible has to not have 0 as an eigenvalue. It says a square matrix is invertible if and only if 0 is not an eigenvalue. We had one where 0 was an eigenvalue, right? Let's take a look at that matrix. With this matrix, we found 0 to be an eigenvalue. So I wonder if this is invertible. How do you check if something's invertible? The determinant is non-zero. Isn't that another theorem? Let's find the determinant of this. We found the determinant of a minus lambda I, but let's see if we could just find the determinant of this thing. Determinant of a is equal to, again, we'll expand in the second row. So 0, this is a plus, minus, plus, so this is a plus 2. And then 1, negative 1, negative 1, 1. And so the determinant is going to be 2 times 1 minus positive 1, and that's equal to 0. So if the determinant is 0, we said that that was not invertible. So the determinant of A is equal to 0 in this case, and so A is not invertible. And then, just to follow this up with a theorem, lambda is equal to 0 was an eigenvalue. Determinant eigenvalue? Well, the way to find the eigenvalues is to find the determinant. So there's some relationship associated with it. Okay, now the big theorem for today is a continuation of the theorem for, we had a theorem for invertible matrices or something like that. They call it the fundamental theorem of invertible matrices. So I don't know if you want to rewrite everything over again, but I think this is the last version of it. I think maybe there's one more. I don't know. I think the first time we saw this, we ended with D, and then next time we saw this, we ended with J or K or something. Now we get to add a couple more things that are related to determinants and eigenvectors or eigenvalues. So if you have an n by n matrix, it doesn't matter what size as long as it's a square matrix, then the following are equivalent. So A is invertible, means it has an inverse. And so we saw all this stuff from before. A reduced row echelon form is the identity, the product, it's a product of elementary matrices. The rank is the whole thing. The rank is n, the nullity is 0, which means the null space is 0. And then the row and the column space are all the Rn vectors, or the whole space. Let's see. So the two new ones are the determinant of A is not equal to 0, which we got from last section, and then this last one that says 0 is not an eigenvalue. So everything else here we've seen before, and then the two new additions to this would be the determinant and the eigenvalue information. So if you're looking for an eigenvalue, you got an eigenvalue is equal to 0, then you know that it's not invertible. And if conversely, if you're looking for a set of eigenvalues and you got none of them that equal to 0, then you know that the matrix is invertible. And a bunch of other things. All right. So that's our big theorem. We don't ever prove theorems in this class. We do sometimes, don't we? We have proven one or two theorems. Now let's take a look at powers. All right, let's take a look at this one. You have a square matrix with eigenvalue lambda, the corresponding eigenvector x, and it says for any positive integer n, lambda to the nth power is an eigenvalue of the matrix raised to the nth power, and then it has the same corresponding eigenvector. The second one, if A is invertible, then 1 over lambda is an eigenvalue of the inverse with the corresponding eigenvector. And if A is invertible, then any positive integer n, lambda raised to the n power is an eigenvalue of A to the nth power. Isn't that like the first one? Oh, positive or negative. So this allows the negative exponents, negative 2 power or something like that. So I'd like to show you some examples of this, but the calculations will take a while. So I was thinking about just maybe putting something in Mathematica, which I thought I booted up, but I guess I didn't. And then taking a look at the eigenvalues and eigenvectors of those things. So let's take a look at an example. I guess since we have Mathematica, we can get any size matrix, huh? How about we do the ones that we already did, like number 10? So number 10 it's invertible, so we can mess around with this matrix. We didn't find the eigenvectors, right? We just found the eigenvalues. I think I can find the eigenvectors pretty quickly. I hope. Zero, 1, 2, 3. So eigenvalues, eigenvectors. Oh, we have an eigenvector of 0 here. Any ideas where this eigenvector of 0 came from? Do you remember what we found for is it for 1? So I don't know if you remember, we just did this problem where we found the eigenvalues quickly because it was what's it called? It's a what? It's an upper triangular, so we found the eigenvalues pretty quickly. And then we decided to dive into the eigenvalue 2 because it has multiplicity, it has algebraic multiplicity of 2. You can see the algebraic multiplicity here, right? Algebraic multiplicity of 2. And then we found that we only found one vector. It had a geometric multiplicity of 1. So these corresponding eigenvectors, these eigenvectors correspond to the eigenvalues in order. And so this 0 vector is, in Mathematica, it's a placeholder to keep the eigenvalues the same, or to keep the eigenvalues in line, or whatever. It's sorted in order from largest eigenvalue to the smallest eigenvalue. So since this thing was 4-dimensional, this thing had 4 eigenvalues, counting multiplicity, they counted this as 0, which says that your eigenvalue of 2, your eigenspace, only has that one eigenvector. It didn't have 2 eigenvectors, so our geometric multiplicity had multiplicity. Our geometric multiplicity was 1. So, and remember, this was 1, 0, 0, 0 was the eigenvalue eigenvector that we found, right? All right, so that's interesting. That's not what this theorem is saying, though. So let's take a look at this theorem. Let's figure out, let's pick an n. Pick an n, any n. Positive integer. We'll start off with a positive integer. 2? That's it? 35. Okay. Can you guys, anybody have calculators up? Punch in 3 to the 35th power. Is that going to be way too big? Oh. Maybe a little too much. What? 5? All right. 3 to the 5th power is manageable, right? Okay. So, let's figure out what a to the 5th looks like. So a to the 5th, oh, this looks like it kind of follows a pattern. It's still upper triangular. I don't know if we talked about a property that if you have an upper triangular matrix and you multiply it by another upper triangular matrix, you're going to get an upper triangular matrix. So the product of 2 upper triangular matrices are upper triangular. So let's take a snapshot of this. So that's what a to the 5th looks like. And if we look at the eigenvalues of this, since this is another upper triangular matrix, the eigenvalues of this is just equal to this, right? So what was 3 to the 5th again? 243. So the e values are again 243, 32 twice, and 1. So those are your eigenvalues. And it turns out that your eigenvectors are going to be the same. 2, 1, 1, 0. So for these two, we came up with only one eigenvector, right? 1, 0, 0, 0. And then for this one, the eigenvector is -1, 1, 0, 0. So without having to do any computations, once we know the eigenvalues and eigenvectors of the original matrix, we can find the eigenvalues and eigenvectors of our matrix that's been raised to a power. And we can confirm that with Mathematica. I think eigensystem of a raised to the 5th power what? This doesn't look right. The other one doesn't look right either. What if we put eigenvectors? What? They changed their eigenvectors. Well, let's not, I don't know. We should. Yeah, let's trust the theorem. It looks like Mathematica might be doing something to find shortcuts to finding the eigenvectors, so maybe that's why we're getting different things. How about the inverse business? Let's find the inverse of this. So the inverse of this matrix looks like this. Should we do this? Let's do this on another page. So this is A inverse. And remember, the A has E values, eigenvalues, 3, 2, 2, and 1. So if this is the inverse, then we should expect eigenvalues of 1/3, 1/2, 1/2, and 1. So let's see if we get that. Oh, I guess we don't need to because this is a diagonal, right? It's an upper triangular, so just by looking at this, so A inverse has E values of 1/2, 1, that's a 1/3, and then a 1/2 again. Okay, so the vector should also match our previous eigenvectors, but Mathematica is going to give us something different. So let's see. Eigenvectors of the inverse of A vectors with an S. Oh, it's the same now. Wait, it's not the same. Is it the same? Did you guys write down the eigenvectors from the last one? Oh, so it is the same. So this one worked out okay. Let me get it copied. The order does matter, but the Mathematica lists them from largest to smallest. So if we reshuffle the eigenvalues, Mathematica would list 1 first because that's the largest, and then 1/2, 1/2, and then 1/3. So that would be your matching eigenvectors. Again, this 1/2 is repeated, so that's why it's listed like that. But that was that the -1, so it looks good. All right, so that one worked out for us, and the other one didn't for some reason, but let's not worry about it. Let's trust the theorem. Okay, any questions? Now, this whole determinant business brings up the polynomial, and the polynomial has a lot of information associated with it. And so there's a lot of theorems that kind of use the idea of polynomials. There's one more theorem. Oh, before I get to doing what I was saying. There's one more theorem to put here. And this one is kind of related to your homework, so I wanted to make sure that we cover it. So suppose we have a matrix, a square matrix with eigenvectors corresponding to some eigenvalues. Notice the m is different from the n because it's not necessarily the same size. So this is assuming that you have some sort of algebraic multiplicity and stuff like that. And x is a vector in Rn that can be expressed as a linear combination of these eigenvectors. So your eigenvectors can be listed like this. Then for any integer k, this is the power of the matrix. You raise the matrix to the kth power and apply x to it, then it's going to be pretty much that linear combination with your eigenvalues attached to it. Whatever that means. This whole thing looks confusing, huh? So, again, some of these theorems look kind of obscure until you start doing a problem associated with it. So I was going to do a problem that uses this theorem. I wanted to do a 2x2 matrix, but let's do this one. So we have a 3x3 matrix. Actually, we don't know what that 3x3 matrix is, but we have some sort of matrix, but we have some sort of 3x3 matrix. We don't know what it is. Is that too small? But we know that the eigenvalues and eigenvectors for those 3x3 matrix looks like this. And then we don't know what A is, but it turns out that we're not going to care what A is. The only thing we need to do to try to solve this problem is to be able to write X as a linear combination of the three eigenvectors. So in other words, we have, can we write X 2, 1, 2 is equal to C1 times the V1 vector plus C2 times the V2 vector plus C3 times the V3 vector. So hopefully we don't, I mean, we can set this up as a system of linear equations because that's what's going to turn out, but can we just kind of guess and see? Looks like C3 is going to be 2, right? For starters. So C2 is equal to negative 2. And what would C1 be left with? 1? C1 is equal to 1. Is that, let's test it out and make sure that's okay. Which one is which? C2 is negative 1. And C1 is 2? 1? Is this going to work now? So 1 minus 1 plus 2, 0 minus 1 plus 2, and 0, 0, and 2. So that looks like it works, right? Okay so far? So now, a to the 20th power, according to this theorem, a to the 20th power times x, or applied to x, 2, 1, 2, should equal to C1, or C1 is 1, times lambda, this is for the first matrix, or the first vector, corresponding lambda 1, so that's negative 3, or negative 1/3, raised to the 20th power, times V1, which is 1, 0, 0. Does that make sense? Just plugging in the formula. Plus C2, which is negative 1, times the lambda 2, 1/3 raised to the 20th power again, times the vector V1, and then C3 times 1 to the 20th power times that last vector. Okay? So that's how you can find this without ever knowing your matrix A. Of course, we can find a way to figure out what A is equal to given our eigenvalues and eigenvectors, but I think we can just simplify this and find out our solution. Any questions? All right, so there's a couple of other problems that are in your homework that's related to some things that I didn't go over, but I think the stuff the theorems that it involves are not in the main part of the book. They're in the exercise area. So you may want to take a look at some of those things in your exercises before you do your homework. So I didn't give you guys the quiz today, and I will post a copy of the quiz for you to download and do at home, and then you give it back to me on Monday. Pardon me? It's a take-home quiz, yeah. Okay? I think that's it. So, oh, the test. You guys want them?